people connected. So, and I think we can actually start. So, our morning session, which is devoted to MBE growth of different nanostructures and nanowires. And the first talk of the morning session will be given by George Sirin, and it's entitled MBE growth of nitride-based nanostructures. Please, George.
Thank you very much, Vladimir. Good morning, everybody who can actually wake up at this early morning, at least from European point of view. And so it's really nice that I have a chance to give a talk here, because at the moment the conferences are not so frequent. And it's nice to see those people who are involved in this business. And good morning, friends, colleagues. Concerning my talk, I would say that the title is possibly too ambitious, and in fact, it's going to be some short stories about particular questions concerning the growth of nitride-based nanostructures, and it's going to be not, let's say, a review talk, and I will mostly show the results we got quite recently, and trying to explain it's interesting for us and what we got during the last years. So this outline of my talk, and the first story will be about the unintentional doping issues which may appear during the high temperature growth, which is typical for gallium nitride or aluminum nitride based nanowires on different kind of substrates. And in my particular case, we are going to discuss the growth on silicon and silicon carbide substrates. Then we are going to move to indium gallium nitride nanostructures based system, and we also will discuss the difference what happened during the growth on silicon or on silicon carbide substrates, and then at the end some conclusions. Okay, concerning the doping issues of the nanowires, so everybody knows now that the nanowires tend to be business stuff. So the nanowires start to appear as a business product, and some few devices start to appear on the market. And that is why the doping of the material is a very important issue, because of the production of these devices. Everybody is interested in, let's say, intentional doping. So people would like to investigate how the doping impurities influence on electrophysical properties of the, let's say, nanowires, nanostructures. But in some particular cases, we should take into account that the doping may proceed in an unintentional way, where we cannot really control what is happening during the high temperature growth. Let's say it's around 850, 900 centigrades, which is typical temperatures, which are typical temperatures for the growth of gallium nitride nanowires. So it's this the beginning of the first story. So for the growth of the nanowires, we now using a small Ribera compact well setup, which is equipped with metallic sources like gallium, aluminum, as well as doping sources like magnesium and silicon, and plasma-assisted nitrogen source. We use different kinds of substrates, silicon carbide, and this stuff is nice from a point of view of basic stuff, but it's practically cannot use for production one. But anyway, to see what are the trends, what are the typical tendencies, we may use simply this setup. For the growth of nanowires, we use different kind of substrates. One of typical one is silicon 111. Another one which we use is the so-called hybrid silicon carbide on silicon substrates. And the growth proceeds in very typical way. So we create somehow the holes which are penetrated to the substrate surface, and then if we open the shutters of desired sources, we may start to grow the nanowires. The first story will be about the growth of gallium nitride nanostructures on this kind of substrates. This is the beginning of the story. I remember it was something like 5 years ago when we started completely different stuff. We would like to investigate the piezo properties of the nanowires, and in this case, we getting the sample from Jean-Christophe Stock, having this gallium nitride nanowires which will grow on silicon with quite small density of them, and also aluminum nitride ions were used to proceed the growth of gallium nitride nanowires afterwards. And in fact, we did not see any significant signal from a piezo electrical point of view. But what we found that these nanowires were, in fact, N-type doped. So even we did not use silicon for the growth of these gallium nitride nanowires. And using EBIC technique, which is electron beam induced current microscopy technique, we also found that not only the nanowires exhibit N-type conductivity, but also the substrates was extremely high doped, at least at the border in between the nanowires and the substrate itself. And we assume that this is due to the very efficient migration of aluminum atoms, which comes from the aluminum nitride ions into the surface. And we found that the profile of this diffusion makes it 50 microns from the top of the substrate toward the center of it. So it means that the growth of gallium nitride nanowires just lead to the unintentional doping of the silicon substrate itself, and it has to be taken into account. So this is the conclusion of the first part, and what we found here that electrical signal was observed deep in the silicon wafer to the depth of up to 50 micrometers, and this is due to the effective aluminum diffusion of atoms into the silicon substrate. Additionally, intentionally undoped gallium nitride nanowires appear to be N-type doped, and we believe it's due to the efficient silicon diffusion from the substrate into the gallium nitride nanowires. So it has to be taken into account when you are thinking about the device application, so that something is happening at the interface between the nanowires and the substrate. And if you consider this heterostructure as an active device component. So you have to think about how to use it or try to avoid it. So next, we are going to discuss a little bit concerning the what is happening with ultra high level of doping of different kind of materials of starting with gallium nitride nanoways. So what we found, for example, if we increase the number of atoms impinged from the silicon source, there is a shift of a Pili line from the exciton in this particular case. And in some extreme cases, when the temperature of silicon source is quite high, we may observe the emission of the exciton, which is beyond the band gap of gallium nitride. And it was explained by the so-called Moss-Boorstin effect, which we can discuss a little bit later. So another part of our work was devoted to the growth of gallium nitride-based nanostructures on hybrid silicon carbide substrates, which we got from the group of Professor Kukushkin. And they developed a technology which allowed them to obtain the monocrystalline quality silicon carbide thin layer on the top of silicon substrate. And the method is based on the heating at a high temperature of silicon substrate in the environment of different gases, which allow them to get this silicon carbide thin layer on top of the silicon substrate. What it also has to be mentioned here that due to effective diffusion of silicon into silicon carbide layer, a significant number of pores appear just beneath this silicon carbide layer, which can be seen from them here or here, and in dependence on the growth parameters used, the number and the density of these pores can be different. And we start growing this gallium nitride nanowires on these kind of structures, and it appears that it's possible. So these are how this nanowires looks like. So here is a thin layer of silicon carbide, these pores, and this on top of them, the nanowires can be grown. So different temperatures lead to different morphologies of the nanowires, and so we can control in some predictable way the density, the height of them. And what also was interesting that the crystallographic quality of the nanowires which were grown on these hybrid structures appear to be bigger or better in comparison to those grown on silicon substrate itself. This also in agreement, not from photoemissions point of view, but from Raman point of view. It was proved from with Raman spectroscopy that the gallium nitride nanowires has better quality in comparison to those grown directly on silicon substrate. What we also found that okay, sometimes we may get planar substrate, but sometimes so-called vicinal substrates, In this particular case, on the surface, we may have different orientation of the facets or the surface. For example, we may have 111 surface and something like 113 surface, and this tilt angle which corresponds to the vicinity of the substrate. And we also see that the morphology of the nanowires are different in the planar surface or on the vicinal surfaces. These are the view how this nanowires looks like, and what it was found later that the photoluminescence properties of these nanowires are completely different. For example, if we carry out photoluminescence from the nanowires grown on singular silicon carbide silicon surface, in this case, we have a typical photoluminescence picture for exciton emission at low temperatures. But if we grow the nanowires on top of vicinal surfaces, the photoluminescence spectra completely different. And sometimes we may get a very strong signal from that part, which is bigger than the energy gap of gallium nitride. And we think this another manifestation of Moss-Burstein effect, where the signal may come from the level which is inside, which outside of this energy band, and it lies somewhere in the conduction band. So we think our assumption was that this is due to the effective silicon migration from the silicon carbide, and mostly from the vicinal part of the silicon carbide into the gallium nitride nanowires. And it was explained a little bit early by Kukushkin and Osipov, and they gave explanation of this effect via so-called Gorsky effect, where the topochemical substitution of atom is likely due to these corners which appear at vicinal surfaces. In this particular case, the surface is quite rough. The surface is bigger in comparison to the singular one, and in this case, we may expect to have bigger silicon diffusion into gallium nitride nanowires. And in fact, it was proved from secondary ion mass spectrometry data, which shows us that we may get very high concentration of silicon atoms in the nanowires and in some interface in between gallium nitride and silicon carbide. And in some particular cases, we may have the number of silicon atoms which is bigger or beyond the solubility limit of silicon in gallium nitride. And to additionally prove this our concept, we measure we did Raman spectroscopy of these samples, and we found that a new peak, which is around 350 reciprocal centimeters, is observed in these particular structures. And using quantum chemical modeling, we found that this feature can be observed if the silicon atoms substitute the the nitrogen nitrous side. And also similar picture is observed if silicon is somewhere in the anti-side state. So another factor which has to be taken into account that if we use the high doping of the materials, we may have the morphology transition from the nanowires to nanotubes. And these are two examples when we use high doping of silicon of gallium nitride nanowires. In this case, we may see clearly that the nanowires are converted into nanotubes. And the similar effect was observed if we grow indium gallium nitride nanowires with a high concentration of magnesium. In this case, we also observe the formation of this kind of hollow inside the indium gallium nitride nanowire. So this is more or less all about the growth of gallium nitride, pure gallium nitride nanostructures. And now we are moving towards indium gallium nitride nanostructures. The aim is very clear. So the indium gallium nitride ternary compounds are direct band materials in a wide band gap range, saying from 0.7 to 3.4 electron volts. Theoretically, it's very nice, and so we may use this kind of ternary compounds to produce effectively the emission in wide range. From ultraviolet to infrared, and which is most importantly in visible range, including the so-called green band problem. So it is known that to get green light or even red line from this nitrogen-based material is still a challenging task. So, and our first experiments which we did show that some kinds we may grow very nice picturesque nanostructures, which we may refer to as nanoflowers. And we were excited to see this kind of structures. And what is interesting here that we did not use any temperature change during the growth, but at the beginning, this indium gallium nitride formed a kind of nanorods. Then, starting from some point, it converted in a more complex structure, which looks like flowers. So, and we found that the interface in between silicon and indium gallium nitride is quite sharp, and so we may see that there are some possibly contrast due to the tension which appeared due to the different lattice constants between silicon and indium gallium nitride. And starting from some point, indium gallium nitride having a Wurtzite phase is converted to silicon blend, thin blend, sorry, indium gallium nitride having much smaller content of indium, but at some next point, again, indium gallium nitride Wurtzite structure can reappear on the side wall of this thin blend segment. And we also check the indium content in different part of nanowires, and what we found that the indium content is different for different parts of these nanoflowers. So it's about 20% at the lower part. Then, as we found before, it converted to the cubic phase, which has much smaller indium content. Then again, the indium content become bigger, and it's more or less constant up to the top of the nanoflowers, except of the small difference, let's say 30–40% of the base of the flowers and the lips of them. Okay, and then so for these particular structures, we use quite low growth temperatures. And if we increase the temperatures, the nanoflowers are completely change their geometry towards the nanowires based one. These are typical SEM images for them. And we check photoemissions properties, and we found that these nanowires, both nanoflowers and nanowires, exhibit very strong photoemissions at room temperature. And the power dependence shows this linear dependence, which cannot be attributed to defect-related luminescence, which has to have some maximum and then saturation of the intensity. And these are typical both for nanoflowers and nanowires. And from the other point of view, the intensity of the nanowires is something like 3, 4, 5 times bigger in comparison to the nanoflowers. And the wavelength of emission is also might be changed. And then we are mostly been interested in the growth of this kind of indium gallium nitride nanowires. And we found that, that in fact, these nanowires has a core shell structure in which the shell of indium gallium nitride, the shell have more or less 0 indium content in it, or it's up to something like 4%. But the core of indium gallium nitride has a much bigger indium content, which may reach up to 50%, which you definitely know, which is inside the so-called miscibility gap, which cannot be easily achieved using just planar technology. And these are typical images, SEM image of this nanowires. As I mentioned, that in most cases, we have core shell structure in which indium content is much bigger in the core in comparison to the shell. And these are typically how looks like behavior of optical properties in comparison to the growth temperature we use. And this very delicate system, and just the change of the 20 centigrades Celsius leads to the very big shift of pale light, say from 450 to 700, if we just change the substrate temperature for 20 centigrades. What is also nice here that we may easily vary the photoemissions from the blue to the red, and it's really good in a view of the challenges which come from nitrogen-based materials in a planar case. You remember this red and green problems there. So we also try to grow indium gallium nitride on different kind of substrates. This example of indium gallium nitride on silicon carbide, on aluminum nitride, on silicon oxide. And I would say that from crystallographic point of view, those nanowires looks better in comparison to those grown on different kind of substrates. And this also in agreement with photoemission study, which show some common features. First of all, we may see that in any case we have the low wavelength band, which corresponds to the core of the nanowires, and also the band corresponds to the luminescence from the core of this nanowires. And if we compare the optical properties of those nanowires, we may find that the nanowires grows on silicon or silicon carbide is preferable in comparison to those grown aluminum nitride or silicon oxide. But at the same time, another feature is that on silicon carbide, the content of indium is smaller in comparison to those grown on different kinds of substrates. And we think it's due to the two facts. First of all, the appearance of the pores just beneath the silicon carbide surface, leading to the different temperature gradient, and because the pores are just something like a vacuum or gaseous stuff, and the transition of radiance is small in comparison to the crystal quality material. Another story is that the lattice mismatch between silicon carbide and indium gallium nitride and silicon indium nitride is smaller, and in this case, the mechanism may definitely be different, and we are now trying to understand why it's happening. So then, if we are interested to grow this indium gallium nitride nanowires, it's interesting to see whether it's possible to do the real device structure based on them. And with silicon is not problem to dope with, but at the beginning we was not sure that indium gallium nitride may be effectively doped with magnesium. And after the experiments we found, yes, we can dope with magnesium, and it appears that these nanowires have p-type conductivity. And we also found that it's very easy, even from just simple SEM measurements, to predict do we have we do the doping of magnesium, and if these nanowires are transparent from current point of view. So we may see that the different contrast of undoped and doped part may be seen here. And we also found that by increasing of the gallium flux on the top layer, which is gallium nitride doped with magnesium, may lead to the reformation of the structure from the nanowires-like to the more or less two-dimensional coalescence on the top of the nanowires. And it possibly a way to produce in more simple ways a top contact for them. And finally, what we did, we produced this kind of prototype of indium gallium cyanide nitride, indium gallium nitride based device. We put active layer inside indium gallium nitride active layer inside gallium nitride nanowires, which were doped on the base with silicon and top of this magnesium. And we put aluminum contact on silicon substrate from the bottom of the substrate. And we also just at the beginning, and our point, we just put the ports of, silver past on top of gallium nitride top nanowire. So we did not any, let's say, special procedure to produce better contact, and this was just to check whether it work or not. And it found that we may get nice IV characteristic of this kind of prototype. And we also got the luminescence, which covers the wide range of the visible spectra, let's say from 450 to 600, which is inside the composition of nitride from, let's say, 25 to 45%, which is maybe one of the way to create this kind of light emitting devices. So this more or less the last part of my talk. So everybody now looking towards the flexible devices, and the most approaches which been used is to embed in a kind of PMMA layer of the array of nanowires and then detach from the surface. But we found that in some particular cases we may use another technique which is very simple. We use this kind of solution which allows us to detach the nanowires array in a very simple way. So if we put the substrate with the nanowires inside this solution, just after 1 minute, the arrays start to detach from the substrate. If we, let's say, treat in this way something like 3 minutes, we may get a complete detachment of the nanowires from the substrate. It's a part of the substrate after the release of indium gallium cyanide, indium gallium nitride arrays from it. And we may even have the flakes of these nanowires just have a tweezer just to move it somewhere, or it may be stored in the solution. And we may then easily transfer from this solution to another kind of substrate like glass or whatever. So I think that it's a nice procedure, a very simple procedure, which allows us to use it for the release of the nanowires arrays in a let's say flakes way, and most probably we may use them for use for a kind of flexible devices. Okay, these are those people who been involved in this kind of study. This Vlad Grich and Rodion Reznik, who've been responsible for MBA growth. Those people who are actively act like a person, very important person who did optical and post growth and TM characterization, as well as I would additionally acknowledge Andrei Osipov and Sergei Kukushkin, who provide us silicon carbide silicon material. And this more or less end. My conclusions are very simple, that during the growth of gallium nitride nanowires at high temperature, the issues which may happen during this growth has to be taken into account, that unintentional doping may appear, that also indium gallium nitride nanowires can be grown in a more or less predictable way, and under certain growth conditions, the composition of indium gallium nitride may lead to the overcoming of bandgap miscibility. And we also develop a method which allows to very easy, in a very easy way, release the nanowires arrays from the substrate and then transfer to any place you want. Thank you very much.
Thank you very much, George, for this inspiring talk. So may I start with my own question? You mentioned at the beginning aluminum diffusion as a possible explanation for N-type doping of gallium nitride nanowires. I take your point that it works for silicon.
No, sorry, it was possibly misunderstanding. Aluminium penetrate inside silicon.
Yeah, I understand, but how it explains N-type doping of nanowires itself?
So this is another story. So we have two fluxes. One flux is aluminium from the top of interface between the let's say nitrogen-based material and substrate. And since aluminium is quite small atom, it may effectively diffuse inside or into silicon substrate.
Yeah, this I understand.
From the other side, silicon may also diffuse into gallium.
So it's silicon diffusion.
Yes,
okay.
Exactly. And which
okay,
is
yeah,
also...
okay. Now I understand. Thanks.
Okay.
Zbig, yes, please.
Yeah, I have a question related to the last part of your talk. I mean, sure. this detachment procedure.
Okay.
Could you tell a little bit more about that? I mean, what part of the structure is etched away during this procedure? Do you use any layering between the? I don't remember what was the substrate in this case. So.
No. Okay. Let me try to explain you. So for this particular case, we used indium gallium nitride nanowires, which were grown directly on silicon substrate.
Okay.
But since the nanowires are growing from the silicon, in our particular case, there is a layer of silicon oxide in between the nanowires.
Silicon nitride.
Silicon oxide, natural.
Okay. Okay.
And in this particular case, the nanowires are touch each other via this parasitic layer of silicon oxide. And this kind of solution allows us to chemically treat this silicon, chemically detach the silicon oxide from the substrate of, from the silicon surface. And then in this particular case, we have this nanowire sitting on silicon oxide layer.
Yeah, but you mentioned you remove silicon oxide. So what keeps this wires together? I mean, so they create
no. These are silicon oxide in between of them. This is a layer of silicon oxide.
Okay. Thank you.
Oh, yeah, so if you are interested, I may just send you possibly the chemical explanation of this phenomenon. We try to explain it, and yeah, I'm not an expert in this chemical formula, so possibly it will be more easy to you to be deeper in details.
Okay, yeah, I will appreciate that. Thank you.
Okay. So, by the way, we got a patent on it.
Okay.
Other questions?
I have a question about the doping order in PIN structures. Have you ever tried to inverse and put P on the bottom?
Not really. Just the explanation was very simple because in the stock we just have silicon N-type substrates. And in this case, if we want to use it as an active layer, in this particular case, we must use it in this sequence. So definitely we are interested to investigate opposite stuff, and now we order different kind of substrate. But you know that for let's say p-type substrate to get its highly doped p-type substrate, it's a problem. And this case, so we try to find a producer which we would like to have the substrate from whom.
Thank you.
So we are planning to do.
Further questions?
Yes, I have one. Professor Sirlin, thank you for a very interesting talk. You showed the figures of nanotube, nanowire growth. Maybe I missed something. Could you tell a little bit more about the physics behind the formation of such nanotubes? Why pores are being formed in the center of a nanowire?
Okay, we have an explanation. I'm not sure it's correct or not. But anyway, what is happening here? It is well known that if the number of these impurity atoms is quite high, in this case, it may change the rate of the migration of main atoms over the surface of the nanowires. And in this case, it may stop or it may enhance the migration of gallium nitride. In this case, we may expect to have the bigger diffusion along the nanowires when the silicon atoms would sit on the sidewalk. It is known that there is a segregation of silicon. Silicon would prefer to sit closer to the surface. And in this particular case, it changed the diffusion of gallium atoms. That's why there is a difference in migration along the surface and due to the direct impingement of gallium. I'm not sure that this explanation is complete, but anyway, it might be a kind of explanation of the effect. Anyway, I think that more detailed study has to be done in this particular case.
Thank you.
Can I make one point here? People from Clermont-Ferrand observed this also formation of nanotubes, spontaneous formation of in-gun nanotubes. But that was, of course, a different H3PE process, and they were grown, I think, on gallium nitride layer. So, but it has been seen also in
definitely we are not those people who discover this. My point was that it has to be taken into account that the geometry might be changed. In this case, for example, if you are interested in contacts, it has to be taken into account because know sure that these hollow places are not the best one for if you are interested in planar contacts.
We still have time for one more question if you want.
I think so. So I'm
well, yes, we have some flexibility.
All right, but possibly
I don't see any. So George, thank you again.
Okay,
so,
thank you very much for your interest.
Yes, thanks. So the session will be continued with a talk of Rodion Reznik entitled 3.5 Hybrid Nanostructures on Silicon, MBE Growth and Properties.
Good morning for everybody. First of all, I want to say thank you to organizers of this beautiful conference for this opportunity to tell a few words about our experimental results. I will say, I will show our results about 3.5 hybrid nanostructures on silicon, about MBE growth and properties of these nanostructures. So after a small introduction, I will say about indium arsenide phosphide quantum dots in indium phosphide nanowires. So such kind of nanostructures are perspective as sources of single photons, I mean quantum dot in nanowires. Also, I will say about another material system like gallium arsenide quantum dots in aluminium gallium arsenide nanowires on silicon. And then I will show very last results about indium gallium arsenide quantum dots in aluminium gallium arsenide nanowires, and just a few slides about other nanostructures, new nanostructures on silicon surface. So in our lab in Alfyorov University in St. Petersburg, we can grow using MBE technique, a lot of different nanostructures, epithelial layers, nanowires, quantum dots on different surface, using different material systems like usual one, gallium arsenide, like another material system like gallium phosphide, gallium nitride, like and other nitride, like George Zirlin said before. Indium arsenide, for example, indium phosphide, and other system. So usually here I want to talk about some usual MBE growth technique. So first of all, we should clean the substrate, maybe by chemical method or inside the MBE machine. We can heat the substrate for oxide desorption from the substrate if we need it. So then usually we spraying some metal on the surface if we need it, if we need catalyzed, if you want to grow through catalyzed droplets. Usually we use gold or gallium for self-catalyzed growth, and gold for trans-catalyzed growth. And then after formation of metal droplets, we open our sources of 3 and 5 materials and grow nanowires on the substrate. So here in my talk, I want to focus on silicon substrate, because the silicon is a key material for electronic, nanoelectronic now. The most of factories use this platform for production of different devices. But we unfortunately cannot use only silicon, because the silicon is non-direct gap semiconductor, and it is so hard to fabricate the optoelectronic devices based on silicon. So in turn, 3.5 direct gap semiconductors are the most suitable material for optical and optoelectronic devices, but we cannot grow high quality epitaxial layer on 3.5 epitaxial layer on silicon substrate because of significant mismatch in the lattice parameters and the difference between the thermal expansion coefficient. So we will have a lot of defects in grown 3.5 layer. So one of the possible solutions to achieve a high quality of the nanocrystals is nanowires growth. So the speakers before said a lot of words about nanowires, Josh, and yesterday. So because of the unique properties, unique morphological properties of nanowires, stress, this mechanical stress can relax, and we can achieve pure, I mean, in terms of crystal quality, pure nanostructure, even sometimes without any defects. So here I present again some example of nanowires, so like it looks like. So nowadays nanowires really perspective nanomaterial. So nowadays a lot of devices based on nanowires already let's say alive in our worlds, like some diodes based on nanowires, solar cell structures for cell research, gas sensors, and other. In our lab, we have I think 3 MBE setups, but in my talk I will present the results about nanowires growth only using this beautiful MBE machine, Reber Compact 21. This is unique machine because it has additional chamber for metallization and cleaning the substrate. So we can use this for cleaning and oxide removing from the substrate, and we can do it not in growth chamber, because growth chamber should be always clean as much as possible. So, but we can use another chamber for these dirty procedures, I think. So all the, and also we can deposit the gold layer on the substrate surface in this chamber. So the growth chamber of this setup is equipped with 3.5 sources like gallium, indium, and aluminium, some basic 3 material sources, and 5 group is arsenide, phosphide, antimony, and nitrite as well. So, and we can dope our growing nanostructures by silicon for N-type doping and beryllium for P-type doping. Also, we have a fast shutter, which can open and closing of some 0.15 seconds. It is useful for quantum dot formation to achieve sharp interfaces between different material systems. Also, it's useful for, of course, some laser growing. During the growth, it is important to understand what the material, what the structure of growing material we have. After growth, it's possible to use some microscope, CM, TM, to understand what we have, but to control and change some parameters during the growth to achieve the needed structure, we can use reflection high energy electron diffraction. Our setup equipped with this heat system, and we control usually what we have zinc blank phase of nanostructure, or your side, or mixed the principal scheme of the electron beam way is present in this slide, and typical heat pattern of in the beginning like cubic, and then after 30 seconds of growth, pure wurtzite. So sometimes the MBE growing groups trying to achieve wurtzite phase of different nanomaterials because of to achieve a new properties of very known material. I mean, for example, like gas, every cubical gas, the properties of cubical gas is well known, but for wurtzite it is not. Let me start from the first material system based on indium phosphide and indium arsenide phosphide. So using this machine, we have grown indium phosphide nanowires on silicon and formed indium arsenide phosphide quantum dot inside this nanowire. So I present here the temperature regime of growth, substrate temperature, which first of all was clean and 450 degrees, and then we deposed the gold at 550 degrees, and then in growth chamber we increase the temperature only for 270, low temperature regime. It is important for silicon technology as well, not to destroy maybe other materials near other materials on the chip. So we use only 270 degrees to grow these indium phosphide nanowires, and then after 15 minutes of growth, we just open arsenide source, but previously close the main shutter of the setup because we want to have a sharp interface between the nanowires and quantum dot, and we just wait some seconds to let the arsenide atom fulfill the growth chamber. So to have a constant arsenide flux on the substrate. So then after some seconds of formation of quantum dot formation, we just again closed arsenide source and continue on indium phosphide nanowire growth. So here we present CM images of such nanowires. We can control the density of these nanowires by changing the gold deposition parameters. So we try to grow nanowires with very low surface density to have the opportunity to study single nanowires. So we try to have some about 1 nanowires per 1 square micrometers. So anyway, we formed these nanowires which have lengths about 5 microns and diameters in the bottom of nanowires about 16 nanometers, and on the top of nanowires about 20 nanometers. And then we examined the optical properties of these nanostructures. So you can see the principal scheme of these nanowires. So we have quantum dot inside. We principally grew 2 samples with different ratio of arsenides and phosphide, arsenide and phosphide inside quantum dots, about 1.8 and 1.5, and we have different 2 PL spectra from one sample and second sample. This is room temperature PL spectra. So this, if we have the spectra at room temperature, it can say us that we have really pure and really good quality structure. So, and the maximum of the peaks from one sample and second sample is different because of different content of arsenide, which we can understand. But the part which correspond to indium arsenide phosphide has 2 peaks, 1 and 2 for both samples. So we suggested that we have much complex structures, not really like this, because during the indium arsenide phosphide quantum dot formation, also indium arsenide phosphide radial quantum well, like some shell, can grow as well. So to confirm it or not, we just using TM technology, TM method. And yes, we can see that we have a indium arsenide phosphide quantum dot in pure indium phosphide nanowires. And also we have this indium arsenide phosphide quantum well, which correspond to the second peak in our photoluminescence spectra. It is important to note as well that we have pure overside indium phosphide nanowire, which is important as well. So, and then we try to achieve the pure structure with only nanowire and quantum dots, and we try to do it with the heating of our sample. So here presents the different PL spectra after heating the nanowires to 400, 450, 475 degrees. And we can see this peak corresponding to indium arsenide phosphide quantum well didn't exist on the spectra begin from 450 degrees. So possibly the material, the arsenide, can evaporate from nanowires, so go to the quantum dot material. So these nanostructures we can which can emit in this range, including 1.3 micrometers, is of course perspective for telecommunication application. And I think in the future we will try to cool down these nanostructures and maybe achieve some single photon properties of such nanostructures. So now I want to say about perspective as well. Material system, aluminium gallium arsenide for nanowires with quantum dots. The most important property of this system is that the gallium arsenide and aluminium gallium arsenide have same lattice constant. So there is no stress between the nanowire and quantum dot. So we hoped that that can lead to really high crystal quality and sharp interface between nanowire and quantum dot. So first of all, we start with growth of aluminium gallium arsenide nanowires on silicon substrate for the first time, using gold using gold droplets. So this is a typical heat pattern after some minutes of growth, so pure overside. And first of all, we try to find the optimal growth parameters for aluminium gallium arsenide nanowires growth. Here you can see different growth temperatures for nanowires from 510 to 560. And we can see that with increasing the temperature, the height of nanowires is smaller, and the parasitic layer is have a domination, I think. So the optimum optimal temperature was found, and it's something about 510 degrees in Celsius. And I think there's that 20 minutes of growth is enough to form nanowires with 2 micron heights, which is enough for most of application. We can see that after 5 minutes we have really nanowires with really low height. So optimal one is about 20 minutes for us. On the next step, we have grown samples with different content of aluminium from 0.1 to 0.9. Here I present only 4 samples. We can see that with increasing aluminium content, the shape, the morphological geometry of nanowires changed. When aluminium content is low, we have straight height nanowires, but then with increasing aluminium content, the height we have, we can grow nanowires only with with a high diameter and smaller height, which we can explain by different coefficient ad atom migration of aluminium and gallium ad atom, and aluminium ad atom blocked gallium migration on the side walls of nanowires, and we have a higher radial growth of the aluminium gallium arsenide nanowires. Also, here present low temperature PL spectra from these samples, these 4 samples, and for all samples we have 2 peaks, low energy peak and high energy peak, low energy peak and high energy peak. So we suggested again that we have a complex structure here with a core with a low content in aluminium and shell with a higher content of aluminium. Again, to confirm this suggestion, we're using TM study, and again. Again, our suggestion was confirmed. We have a core shell, spontaneous core shell nanostructure with a low content in the core and high in the shell, because we have at least 2 mechanisms of nanowire growth. The core can grow via liquid, vapor, liquid, solid mechanism under the gold droplet, but also we have some radial growth because of aluminium ad atoms, which is higher content of aluminium. It's important to note again that we have good, sometimes pure Wurtzite structure of aluminium gallium arsenide nanowires, which is not well known in nowadays. The next step, we formed aluminium gallium arsenide nanowires with aluminium with gallium arsenide quantum dots on silicon substrate, just closing aluminium shutters for some seconds. The principal scheme, the picture of such kind of structure present here. So this is the gold particle at the top of nanowires, and the quantum dot inside the aluminium gallium arsenide nanowires. So after the growth, we didn't find any difference in morphological parameters of nanowires, but in TM, we can see these gallium arsenide quantum dots inside aluminium gallium arsenide nanowires, which for sure confirm the gallium arsenide quantum dot formation inside nanowires. So after that, we studied the optical properties of these nanostructures by macro photoluminescence method. So this is PL spectra from arrays of nanowires. We can see that we can grow the quantum dots inside nanowires with a different content of aluminum, but they can emit in the same wavelengths, have the same energy of radiation. And at the same time, in the similar, in terms of content of aluminum, in the similar nanowires, we can form different quantum dots by changing the size of quantum dot. It can emit on different wavelengths. So it means that we can grow the nanostructures with a preliminary determined band structure. So we can control band structure of nanowires like barrier and the quantum dots like emitter, like basically emitter. After this, in DTU, we start to study single nanowire within this quantum dots. This quantum dot, here we have small principal scheme of again of these nanowires with different quantum dots. We have 5 seconds on formation, 7 seconds on formation, and 15 seconds. So, and again, even from single nanowires, we have different energy of emission from the quantum dots from 750 to 790 to 800. So it means that we can change our emission from in this wide range, and we have really thin lines in our photoluminescence spectra, about 30 microelectron volts. It is easy resolution of setup in DTU. So to understand what is the real length width of our peaks for photoluminescence, so we use a technology with rubidium resonance. The principal scheme of this method are shown here. So we have emitter, our emitter, then rubidium vapor cell, and then detector. And after radiation going through this rubidium cell, we have this kind of signal in our detector, and after approximation we can calculate that we have the emission length is about 10 microelectron volts. Is absolutely records for these nanostructures. So it means that we possibly have really sharp interfaces and good quality of our nanostructures. Finally, we have done after correlation measurements and have these results in 0 time of G function 0.19. This is enough. It is enough, I think, to say that we have single photon sources. So it was done in DTU as well. And finally, we have not only single photon sources, but high brightness single photon. We have really bright single photon sources, because this number in counts per second is really high. This is new results, because for most of application, the directivity of emission is really important. And in DTU as well, we have measured the PL intensity in different direction from standing on the substrate nanowires and lying on the substrate nanowires. And we have found that the PL spectrum peak from the standing nanowires is I think two number of magnitude higher than from lying. And then with the help of Mikhail Kolesievsky, we built some theory, and you can see here in this corner the directional diagram for such kind of structures for aluminum gallium arsenide nanowires with gallium arsenide quantum dots. And you can see even if we don't have the fundamental optical mode, HE or HE11, we will have the directional radiation about some 22 degrees to axis of nanowires. So we have directional emission from these quantum dots. Also, this is very last results, and well, to increase the number of applications for such structures and to increase the wavelength range of emitting of quantum dot emitting, we tried to form indium gallium arsenide quantum dots inside aluminum gallium arsenide. So changing the indium content and size of these quantum dots, hopefully we can control, we can change the energy of emission and maybe reach 1.3 microns as well, 1.3, 1.5. So we have grown these nanostructures. You can see TM. It looks like usual aluminum gallium arsenide nanowires on silicon, and then you can see TM of this stressed, of course, nanostructure. So this is quantum dot. This is again the indium gallium arsenide quantum well. For us, maybe parasitic quantum well, but let's see. In this case, we have again room temperature PL spectra from these nanostructures from aluminum gallium arsenide somewhere here, but here from indium gallium arsenide. This is PL spectra from 77 Kelvin. So changing the size of these quantum dots, we can change the energy of emission again, and we can see that we can really change the quantum dot size. So again, I think in the nearest future we will use helium temperature to see if we have some sharp lines from these nanostructures. And also already we have grown indium gallium arsenide quantum dots inside aluminum gallium arsenide nanowires at low temperature with about content of indium about 80%. So which we can't achieve in gallium arsenide nanowires at 580 degrees. So also so we wanted to use another materials to increase the number of application again, and have grown aluminium gallium phosphide nanowires with aluminium gallium phosphide quantum dots. It's some kind of new results as well. So you can see in CMMH we have not so simple morphology of the nanowires. It is because we think that this is because the indium participation in the growth, the nanowires can change direction at some cases. But anyway, at low temperature we have photoluminescence from the quantum dots. It's from quantum dots for sure, because the wavelengths of both, because the 550 nanometers is bigger than the wavelengths of both aluminium phosphide and gallium phosphide. So yes. And I want to say a few words about other nanostructures on silicon, which we have grown. So a lot of groups try to grow homogeneous gallium arsenide nanowires on silicon. I mean, homogeneous in terms of diameters or length and length of nanowires, using some special procedures, for example, like etching silicon oxide, native silicon oxide layer by gallium droplets, and then form gallium droplets again in these holes and grow nanowires, like some cheap analog of lithography maybe. But to evaporate the gallium from the substrate, we have to increase the temperature significantly of the substrate, which is important and critically for silicon technology, as I told before. So, and we decided to use not gallium droplets, but indium droplets, because indium, it is much easier to evaporate indium from the substrate, and we have done it. We evaporate indium on the surface with native oxide, then wait some minutes to etching, crystallized by arsenide these droplets of indium, and then evaporate it at lower temperature. And then in these holes form gallium droplet, and have grown these beautiful gallium arsenide nanowires with the homogeneous diameter and length of nanowires, and which is important, there is no peak in our EDX corresponding to indium, and so it means that we fully evaporate indium from the substrate. Also, again, low temperature is important for silicon technology, and we have grown low temperature alkalized indium arsenide nanowires only at 270 degrees via vapor solid mechanism, because this nanoparticle due the growth at this temperature is not liquid, it's solid. So, and we, in this case, we also had a higher growth rate of nanowires to compare with vapor liquid solid mechanism, which was described by Vladimir Dubrovsky and Alexander Koryakin. It is important to know again that we have pure word-side structure of indium arsenide nanowires. And finally, this is my last result, my last slide. Also at low temperature, even 220 degrees, we have grown indium gallium arsenide nanowires on silicon with a 50% composition indium or gallium. Like George Zilin said in his talk for indium gallium nitride about miscibility gap, the same story with indium gallium arsenide nanowires. It's not so easy to achieve 50% of content of indium content in this solid solution, but growth of nanowires, of nanowires, we can achieve this content. So this is results of our UDX measurements. We really have the same content of gallium and indium inside, but also have a not so simple structure with a core shell with different content of indium and gallium in the core shell. And also Vladimir Dubrovsky has described this system. So this is my conclusion. I can say that we have grown different quantum dots in nanowires for different applications, like indium phosphide, indium arsenide phosphide system, which is suitable for telecommunication applications, aluminium gallium arsenide material system, which is silicon, which are single photon sources, with a high brightness, with a record PVHM of PL peaks about 10 microelectron volts, and we have grown different as a different perspective 3.5 nanosystem based on nanowires of quantum dots on silicon. So thank you very much for listening to me.
Thank you very much, Rodion, for this excellent talk. I have a question. So most of your Algas nanowires are strongly tapered in the top sections. Yeah?
Yes.
So what is the reason for that? Is it due to a shell forming after the cylindrical core has been grown?
Yeah, you are right. You're absolutely right. They think the same about this phenomena. Because, like to say, the bottom of nanowires, like alive or present on the substrate, much more time than the top of nanowire.
Yes. So it's because of the shell, yeah? Just
Yes.
growing after. Okay, thanks. Other questions, please?
And sorry, because of this phenomena, we try to measure aluminum contained in the core of nanowires on the top of nanowire.
Thanks, okay. Manas, yes, please.
Yes, thank you very much for it. Was a very nice talk and very rich in results. So I have two questions, if I can. So one is, have you quantified the sharpness of the interfaces in your gallium arsenide quantum dot inside the Algas nanowire? So from the TEM, it looks, of course, nice, but do you have a...
It's really, so it's not easy to do it because the small contrast between gallium arsenide and aluminum gallium arsenide materials. So we can say about this only due to our sharp lines. So.
Okay, and then the second one is this method with etching the silicon oxide with indium droplets. What was the annealing temperature? And how do you know that the nanowires finally grow from the spots where the droplets were?
Answering your last question, the density of the holes and nanowires is the same, as the same. So, and as I remember, maybe now I'm not correct, but this is something about the temperature of growth of gallium arsenide, so about 500 degrees. So we using this temperature, we can evaporate indium from the substrate.
Okay, very nice. Thank you.
Alexei, yes, please.
Yes, thank you. Radion, thank you for the inspiring talk. I have a small question. Since quantum dots have different composition from the mother nanowire, they should create some mechanical stress. And what is the estimated magnitude of this stress? And does it somehow affect the growth of a nanowire itself or luminescence spectra of quantum dot, or the stress can be completely neglected?
Thank you for this good question. First of all, in case of aluminum gallium arsenide and gallium arsenide material system, there is no stress between these two materials. Yeah. So again, but in case already in if we add indium to the solid solution of the quantum dots, of course we have stress. And with increasing of indium content, the stress increases too. So you can see on this TM image, this stress black field. So of course it can affect the quality of quantum dot, but hopefully because of the small size, we will not have this effect. Also, the stress effect on the energy of radiation, like the colleges have shown in his publications. So we will have the shift of photoluminescence to the, as I remember, it depends on which materials lattice parameter is bigger. So in this case, as I remember, we will have a shift to high energies.
Mm-hmm. Oh, okay, thank you.
Further questions? I don't see any, so let's thank Rodion again. So the last speaker of the session will be Zbigniew Zitkevich with a talk entitled Mechanisms of Self-Induced Nucleation and Growth of Gallium Nitride Nanowires by Plasma-Assisted MBE.
Okay. Okay, good morning, everyone. Okay, I will try to share my screen. Is it visible? Do you see my
Yes,
slides?
we can see it. Okay, no problem.
Okay, great. So, good morning, everyone, again. First, I'd like to thank both chairs, I mean, Vladimir and Frank, for inviting me to this meeting. Well, I wish we could meet in person, but as we did some 3 years ago, but apparently life is much more complicated than we expected. But I'm still optimistic that next meeting will be real one, not using internet connections. Okay, here I'm showing you. Okay, here I'm showing you outline of my talk. So I will. The first part, I will focus on self-induced gallium nitride nanowires growth on non-crystalline substrates. This is a large topic, but in particular, I will focus on nucleation and growth mechanism of these wires on two substrate, which is one is commonly used nitridized silicon, and the other one is silicon coated with amorphous aluminum oxide. We would use quadrupole mass spectrometry studies just to get a deeper insight into the mechanism active during self-induced growth mechanism of such wires on non-crystalline substrate. During my presentation, a question will appear: what's the origin of enhanced gallium nitride nanowire nucleation on this amorphous aluminum oxide films? And I will answer this using XPS studies. Then I will switch to selective area growth, and I will show you that this buffer layers can be efficiently used as very nice nucleation layers in selective area growth. This will give me a chance also to discuss importance of gallium atom surface diffusion and its importance in selective area growth. And the last part, I will switch to again to silicon substrates, and we will study effect of mixed polarity, which is commonly observed in gallium nitride nanowires grown on silicon. We will use Kelvin force probe microscopy to check what's the polarity and uniformity of polarity of nanowires on such a substrate. In particular, I will show you that residual islands of residual silicon oxide may lead to reversal of nanowire polarity on silicon, and this might be the origin of mixed polarity effect as a general one. Okay, so the process I will be talking about is the following. This is just a sketch. We have MBE, nitrogen-rich condition, no catalyst. We have a substrate. We deliver gallium atoms, and then under nitrogen-rich conditions, gallium flux controls the growth. At the beginning, this gallium atoms just migrate on a surface trying to create a stable nucleus as large as when large enough nuclei is formed, they are thermodynamically stable, and I will show you that there is a shape transition from such an island into the nanowires. So actually this proceeds in two steps: nucleation and then growth. And in my talk, I will try to show you that we can have a insight into this processes. Usually, I mean, the most common substrate is silicon, and what people usually do, they take a silicon 111, deoxidized. So in the red pattern, you see 7x7 surface reconstruction, which is believed to be a fingerprint of really clean silicon surface. Whether or not this is the case, I will discuss later on. Having this surface, people usually open gallium nitrogen sources at the same time. So there's nucleation nanowires, and finally, this kind of pattern is visible on the screen, which corresponds to the nicely ordered nanowires on the surface. However, there's a problem that if we consider bonding energy of nitrogen with silicon and gallium, you can easily see that silicon-nitrogen bond is much stronger. So if we open both cells at the same time, there will be a competition between nitrogen reaction with silicon and gallium. And this is something we want to avoid, because there are some reports showing that in this case, silicon nitride film, which must form, I mean, we cannot avoid this formation of the silicon nitride film on a surface, is rough. So instead of, I mean, leaving the things as they are, we just introduce additional step, which we use before real growth. So we expose our substrate, the oxidized substrate, to nitrogen flux just to create silicon nitride film on the top of the surface, and then only then we start growth of nanowires. And this is the results of such a procedure. Gallium nitride nanowires, which usually are, let's say up to 3-4 micrometers long, pretty dense. Density is difficult to control. And on top 10 images, you see that there is this silicon nitride film in between silicon and gallium nitride. It's usually, you see it always also here. This is something like 2 nanometers thick silicon nitride film. This nitridation is self-limited, so usually it goes to 2 nanometers and then the process stops. No dislocations at this interface with silicon nitride. So I will come back to this point later on. Unique feature of these wires is that independently on the orientation of the silicon substrate underneath, whether this is 001, 111, or even on multicrystalline silicon, we always have nanowires which are perpendicular to the surface or to the local segment of the surface. And this is just because of presence of the silicon nitride film in between. So these wires do not feel orientation of substrate underneath. In that sense, the term gallium nitride nanowires grow on silicon is not precise. Actually, these wires grow on amorphous silicon nitride, not on silicon. If we introduce artificial aluminum oxide layer on the surface of the silicon, then we also have observed this, similar perpendicular wires independently on the thickness of this aluminum oxide film, which can be, in this case, 15 nanometers, so we can go to up to 2 nanometers. These wires are perpendicular not only, physical, as observed in scanning electron microscope, but also X-ray diffraction shows that C-axis is perpendicular to the surface with precision of plus minus 1-2 degrees. And this is, as mentioned, because of presence of the silicon nitride film in between. And in my talk, I will show that this is really important to keep in mind that these wires grow on amorphous substrate. So in general terms, we want to understand how this growth process of such amorphous substrates take place. For that, we will, in my talk, I will compare two systems, in which one is a silicon which is exposed to active nitrogen. So the silicon nitride film is formed. And this is a standard substrate used for MT growth of gallium nitride nanowires. And the other one is a silicon with thin film of amorphous aluminum oxide that was deposited on a silicon by atomic layer deposition. Okay, and for getting insight into the processes going on the surface, I will use two techniques. One is quadruple mass spectrometry. The very simple technique, you take out one fusion cell from your machine, you put head of spectrometer right in the position of the cell, so you measure line of sight. And what the spectrometer is calibrated in such a way that measures flux of gallium that is desorbed from the surface. So we deliver some gallium to the surface, part of this gallium is desorbed, and this is what's measured by the system. And in real life, it looks like that this is this red curve, this is a signal that we measure. At the beginning, there is all the gallium delivered to the substrate is desorbed, then desorption is decreased, as you see here. But since we know exactly how much gallium we deliver to the substrate from the simple mass balance, we can calculate amount of gallium that was incorporated into the crystal. This is this green curve. So the process like that. When we start growth and we open gallium cell, at the beginning, there's no incorporation of gallium into the crystal at all. Then incorporation increases, meaning gallium nitride starts growing on the surface, and then there are next steps. I will explain them in a moment. Okay, so this is again the same profile. And what I'm going to do is to explain you meaning of these various parts of the profile and correlate them with some images of surfaces. So we just stop growth at particular times, and this gives us insight to the state of the surface, so we can distinguish three stages during growth of nanowires on such a substrate. First one, which is marked here, and this green field, there is no incorporation of gallium into gallium nitride at all. So if we have a look on a sample S1, which was grown for a very short time before increase of QMS signal, there is nothing on the surface. But as soon as the signal increases, we see first nuclei that appear on surface. So the first stage is incubation period. This is the period during which gallium add atoms migrate on the surface, trying to create a stable nuclei. Then, when the nuclei are stable, you see the first one appeared here, just at the very beginning. Then density increases. So this is a nucleation period, and then there is a period when these wires elongate, and next steps are in the game. So these are again same images of these two samples grown during growth was terminated during the nucleation period. Very beginning of nucleation, you see that this nuclei have a shape of a cap, and then density of wires increases. Some of them have already shape of nanowires, meaning on the same piece of the wafer we can see both this cup-shaped islands and nanowires, meaning that there must be a shape transition in between from one shape to the other one. And we have studied this effect more precisely just by measuring on the same wafer diameters and height of cup-shaped islands, these blue points, and nanowires neighborhood, which are green points. And you see that there is some specific dimension of the island when this shape transition takes place. And this is explained in such a way that when the island has such a shape, surface energy is high because it contains many high index planes. So at some moment of time, it's better for the system to transfer shape into such a nanowire shape, because then total surface energy is lower. So driving force for this transition is anisotropy of surface diffusion. And the same thing was earlier observed for growth on silicon nitride by Consoni. The only difference that we observed is a different critical size of the island when this shape transition takes place. Okay, so this gives me a chance to make a short comment. To compare this behavior on a amorphous substrate and on a crystalline substrate. So I took a case of silicon gallium nitride nanowires growth on aluminum from Consoni paper. In our case, as mentioned, we have this cup-shaped island. We have transitioned to nanowires. Nothing special happens. While if aluminum nitride is used, then the process is a little bit more complicated, because at some stage of evolution of this pyramid, this location appears here, which moves to the middle of the wire. So what I want to tell you is that there is a difference between growth on non-crystalline substrate, where epitaxial constraints are very weak, and nucleation on crystalline substrate, where we have all phenomena related to lattice mismatch, generation of misfit dislocation, etc. Okay, and finally so this was this nucleation stage, and finally we are at the stage of elongation. So we get nice system of nanowires. This curve decreases here, and this is because we observed at some stage coalescence of wires, and this is how we explain this decrease here. Okay, what's important in the story is that this green profile that we have here, we can feed using analytical formula. I'm not giving this formula right here because it's boring, it's not important for the topic. But we have an analytical description of this profile, and by fitting this equation to the experimental profile, we can measure in particular value of incubation time. This is time needed in QMS it defines such a way that more or less half of these islands are created already, and we get from fitting we get this value. As an important part of this work that's listed here is that we measured how this incorporation time changes with nitrogen flux, gallium flux, and surface temperature. This is important if you want to control the process. You need to know how the system reacts to the fluxes and surface temperature. Having this knowledge, we can ask a question, okay, if we take this substrate with aluminum oxide, what is the range of growth parameters under which we create compact layer, we create nanowires, or there's no growth at all? And to answer this question, we create this kind of growth map in which here we have gallium flux, growth temperature, nitrogen flux is fixed in this case. And using this formula, we try to fill this map with some boundaries. First boundary is right here. What does it mean no growth? We have decided that if incubation time is longer than 3 hours, then the growth is useless, impractical. So we say, okay, we put 180 minutes here, and this allows us to draw this line. This is the regime when we say, okay, there's no growth of gallium nitride at all. Now, how to grow compact layer? On the contrary to growth of nanowires, if we want to grow compact gallium nitride layers in plasma acid MBE, we need effective gallium to nitrogen flux 1 or larger than 1. Effective meaning not impinging fluxes, but real fluxes, real amount of gallium existing on the surface. So we quite independently, I'm not showing these results, we measured gallium desorption as a function of temperature from nanowire airways. This is included. So this condition gives us this boundary. Okay, and now let's try to compare this with experiment. We grew several samples, and these 3 green points, these are nanowires for which incubation time was much longer than 180 minutes that we declared here. These 2 points are red points, let's squares, are compact layers, as we have seen from some images, because of course after each growth we studied the surface using scanning electron microscope. And all this blue inside, these are nanowires, as also seen in some on some images. So we have a really very good agreement of experimental and experimental data and our expectation from calculation. Now let's have a look on the same thing on silicon nitride. This is a map prepared and published by Sergio Fernandez Garrido. So again, you have this compact layer regime, no growth, and nanocolumns in his case. In order to make any comparison, we just adjust axis, and you see that on silicon nitride, this is the range of parameters available for nanowires, while on aluminum oxide, this range is much wider. So this tells us that aluminum oxide buffer is preferred over nitride silicon, since it enables shorter incubation times and much wider range of parameters under which nanowires can be formed. I told you that, okay, I showed you that we use quadrupole QMS for studying the processes, but the same can be done by read. And then what we do in this case, this is a final read pattern. We know where this spot is going to appear. So from the very beginning, we monitor intensity of this spot, starting from the point when we open gallium cell. And similar to the QMS profile, we see incubation, so there is no gallium nitride in the surface at all, increase nucleation stage at all. So this tool can also be used for monitoring evolution of gallium nitride on the surface. What's important for us is that if we make this comparison, you easily see this under the same conditions. Growth on silicon, nitrate silicon, and aluminum oxide. As I mentioned, incubation time on aluminum oxide much shorter. We have studied this dependence of this read measured incubation time on gallium flux and temperature. So these are on both substrates. And then Vladimir was kind enough and helped us to develop a model that correlated this power parameters P, which describes how the incubation time depends on the gallium flux, with some atomic processes in the surface, in particular with energies of gallium diffusion, bonding, and desorption. And final conclusion of this work is that if we have growth on silicon nitride P equals 2, which corresponds in the model to the nucleation rate, which is limited by gallium diffusion and gallium atom concentration. So this is a kind of homogeneous gallium nitride nucleation. On the contrary, if we consider this aluminum oxide buffer P equals 1, and this corresponds to the situation in which we have external nucleation centers. So gallium nitride nucleation is heterogeneous, and then nucleation rate is limited by density of those centers and their efficiency to capture gallium. Okay, so we see the difference between these two cases. One is homogeneous nucleation, the other one is heterogeneous nucleation on aluminum oxide. Question is, what is the nature of centers that induce nucleation of gallium nitride on this aluminum oxide fields? Well, we spend a lot of time studying surface morphology using AFM, TEM, and all these tools available. And point is, we do not see any surface morphology features as pits, steps that might locally capture gallium and in this way enhance nucleation rate of nanowires. I mean, this is the process well known for gallium arsenide nanowires growth on silicon dioxide, for instance, when there are pits in silicon dioxide where gallium collects at silicon dioxide and nanowire forms there. We do not see any such features in our case. What we see instead is that incubation time strongly depends on time of exposure of aluminum nitride buffer to nitrogen plasma before growth of nanowires. So this is the example. This is again read signal profile. If we open gallium and nitrogen cells in the same moment, this is incubation time, which is something like 27 minutes. In this case, we exposed this buffer to nitrogen plasma for 20 minutes at the growth temperature, and only then gallium was opened. And you see that that incubation times become shorter and shorter. This means that there must be a kind of reaction of aluminum oxide with the nitrogen plasma that leads to creation of some centers, which later on acts as nucleation centers for gallium nitride. And this is actually a very well-known phenomenon, because in MOVP of gallium nitride, it's well known that it's useful to expose sapphire substrate to ammonia flow at high temperature, because then aluminum nitride ions are created that makes nucleation of gallium nitride easier. So question is if this is really the case in our situation. To answer this question, we have done XPS studies. So experiment was such that we first we annealed our substrates in an MB chamber in ammonia, in nitrogen plasma flow at high temperature just to simulate more or less MB growth conditions. And then we studied the samples just to see how and how much nitrogen got incorporated to these films. And you see results here. Crystalline sapphire was used as a reference. And these are two cases for amorphous aluminum oxide films. For both of them, incorporation of nitrogen to film is much, much easier than to crystalline sapphire. And to be more precise, we have also, here I'm showing you 1s line of nitrogen from XPS, and this is crystalline sapphire exposed to plasma for 80 minutes. And this we see two signals. One is aluminum nitride, commonly observed, and the other one is aluminum oxynitride, which is also quite often observed. This crystallized in single structure. But so surprise is here, because when we consider incorporation of nitrogen to aluminum oxide films, we see also aluminum nitride, aluminum oxynitride, but also additional peak, which is aluminum nitride that crystallize in rock salt structure. So having this, we know from our experiments that on crystalline substrates, we do not have nanowires under our growth conditions, while on amorphous aluminum oxide, these nanowires appear. So this gives us a hint that most probably this compound created during nitridation of aluminum oxide might be responsible for, may act as a heterogeneous nucleation center. Of course, right now this process is not finished. We are at the stage of correlating quantitative results of nucleation kinetics with concentration of these phases. But okay, this is a hint that something is going on, but this phase must be considered. Okay, I showed you that aluminum oxide is efficiently used for growth of nanowires, so why not to use it for selective area growth of such a wires? And I will show you two examples that this efficient nucleation layer. First example is we just take gallium nitride substrate with aluminum nitride or aluminum oxide stripes, and we just grow nanowires at typical growth conditions. Here you have result. On this gallium nitride part, we have a low quality gallium nitride because we are growing at not very high temperature and nitrogen rich conditions. So this is not while planar growth requires gallium rich conditions. So quality of the GAN is pretty low. But here we have a very nice nanowires. So again, this example shows that aluminum oxide layer promotes formation of nanowires. Now, we want, of course, to control this growth in such a way to get as much as possible gallium incorporated into nanowires while keeping this parasitic film as thin as possible. So question is how to control ratio between them. And answer is simple. We just assume that thickness of compact layer is proportional to gallium flux. So thickness changes according to this green line. While at this moment, this assumption, I will come back to this later, we assume that nanowires grow under locally gallium-rich conditions, so the length is proportional to nitrogen flux, and time, which is, we need to subtract time needed, delay of nucleation onset incubation time. So we have this line, and we are looking for this range of parameters. We know how incubation time depends on growth parameters, so we can put this right here. And we calculate aspect ratio, which is the ratio of thickness of, length of wires to thickness of compact layer. And having this, we create a map. Nitrogen flux, gallium flux, temperature is fixed, and these lines are shown calculated values of this aspect ratio. And as you see, if we want to put as much gallium to nanowires instead of the layer, we need to go to nitrogen-rich conditions. Even more nitrogen-rich conditions. We need to either increase nitrogen flux or reduce gallium flux. And how it's in practice? Okay, we grew these three structures under these conditions, and here you see the experimental value of aspect ratio we measured on the substrate on the structures, and this feels very nice. This should be 2.1, and this a little bit more than 2. This is fine. Yeah. So under this condition, our model works. However, if we go too far, this is wrong, because we do not have we lose agreement. Measured aspect ratio is 1.7, while we expect something like 3. What's wrong? Well, our assumption is wrong. This layer, these structures indeed grow under locally gallium-rich conditions, which appear at the top surface of nanowire due to the diffusion of gallium atoms along the side walls to the top surface. However, if we put too much nitrogen or too low gallium fluxes, then this condition that we put into the model does not work. Okay, in addition, we notice when studying the structure, have a look on this cross section. This is this aluminum oxide film. This is this compact layer, that there is additional extra edge growth on this part, while on the other side of the boundary, nanowires are thinner, are shorter at the edge. And this tells us something about surface diffusion of gallium atoms. Explanation is the following. Gallium nitride here nucleates immediately, because this is just a homoepitax, while there is some time needed for appearance of first gallium nitride nuclei at that part. During this incubation period, gallium atoms from this side diffuse are captured by this growing gallium nitride, and because this growth is gallium limited, we have extra growth in that part. Simultaneously, concentration of gallium atoms in this part on a stripe decreases, so incubation time increases here, and wires are short. Okay, this was a kind of a little bit academic exercise, because these structures, you see this aspect ratio low, so they do not have a very practical meaning. But we can do the same with when covering the side part with silicon nitride. And because we know that incubation time on silicon nitride is much, much longer than on aluminum oxide, we can choose conditions in which incubation on a mask will require something like 3 hours or 5 hours, while incubation on aluminum oxide is still at reasonable time. So having the structures, we get perfect growth selectivity as required for application. One thing is important here. If you have a look on a cross section of such a stripe, you see that wires close to the edge of the stripes are longer than the middle. So this is quite opposite behavior than that observed previously. And here you have a plot showing how this length of wires changes with distance from the edge. Yeah, this is distribution across the stride, and differences are pretty large because the difference between length of nanowire here and the middle is something like 150 nanometers. Moreover, what we notice is that this inhomogeneity of nanowire length strongly depends on the width of the stride. So if we measure here the edge, it doesn't matter too much how narrow is the stripe. We start from 8 up to 100 nanometers, more or less. This length of nanowires here, this remains the same. While here in the middle, at the beginning, nanowires are much shorter than at the edge, and then their length increases. So later on, right here, we get uniform length of nanowires. Okay, question is what's going on here? And of course, again, gallium surface diffusion is our suspect. But question is at which stage this gallium diffusion takes place here? In order to answer this question, we have considered various scenarios, but this experiment gave us a final answer. This is growth interrupted at the very beginning of nucleation. So when the first nuclei appeared on the surface, and then we studied distribution of these islands across the stride, meaning their size and density. And here you have a plot showing that here close to the edge, these islands are larger and more dense than in the beginning, than in the middle. So this tells us that growth uniformity starts from the very beginning of nanowire nucleation. And this led us to the conclusion that diffusion scenario is something like that, that at the beginning, gallium is delivered everywhere, but as soon as the first gallium nitride island appears here, then it starts sucking gallium from the mask. So this islands get more gallium than the islands in the middle. And again, we are grateful to Vladimir and Dr. Sokolowski for developing a model explaining this. Describing this phenomena. All these lines which are here on the plots, these are results of calculation, and fitting gives us experimental value of gallium diffusion length of aluminum oxide stripes, which equals to 600 nanometers. Okay, general comment is that nucleation kinetics depends on the size, and this is important to keep in mind. And the very last time, Vladimir, do I have still 3 minutes, 5 minutes? Hello?
Yeah, you have
Okay,
5 minutes, no problem.
So I will continue with the growth of nanowires on silicon substrate. And as I mentioned, important parameter of this of gallium nitride itself is polarity. And what you want, because it determines direction of electrical field inside, and this is important for electronic properties, this wires. And I'm going to show you that interface between, this interlayer that sits between nanowires and the substrate itself determines not only growth kinetics, but also properties of wires, in particular, uniformity of polarity inside such an ensemble. So what we did in cooperation with Anna Cross from Valencia, we grew some samples, and then Anna analyzed them by using Kelvin probe force microscopy, which basically measures a contact potential difference between between the tip and the nanowire. And two values are expected for nitrogen and gallium polar phases. And this is the experimental result. In this particular case, silicon substrate was prepared by so-called HF dip. This is a very popular procedure, because the only thing you need to do is just you put your wafer to the diluted HF for a minute, then you take it out dry and transfer in air to the machine. And protection mechanism is such that it's well known that during such a procedure, surface is coated with hydrogen film that is supposed to protect the surface against oxidation during the transfer to the vacuum system. So this is how we prepared our substrate. We saw very clear 7x7 weak pattern prior to growth. So we expected, okay, we have a clean surface. But then as came result from Valencia, distribution of this contact potential difference along wires, and you see that majority of them are gray, they are nitrogen polar, but there are some of them which are black, and these are gallium polar. In this particular sample, or in general, when we use this procedure, we noted that as high as 18% of nanowire exhibited reverse polarity. So they are gallium polar instead of being, as expected, nitrogen polar. And in this work, we checked several recipes of cleaning silicon substrate prior to growth using RCA clean, gallium, cleaning, deoxidation in gallium flux, etc. They help, but the best results, very complete elimination of mixed polarity effect, we obtained only when using high temperature oxide desorption under ultra high vacuum. So clean surface, when you just have a, well, you need to have a wafer from good vendor, and without any treatment, you just dissolve oxide from the surface. You need high temperature heater, which is not always available in the MBE machine, but it's really works. Okay, now question is how we explain, okay, if there must be some oxide left on the surface, and how it reverse polarity. And this we will refer to our previous paper, in which we used also HF treated substrates. This was silicon 001 in this particular case. And we observed that quite often we have in such a substrate two systems of nanowires. One system are these perpendicular ones, standard as expected, but we also observe this kind of inclined nanowires, which are perpendicular to the 111 plane in silicon 001, so they are inclined to the surface. Careful studies of the system with TAMs showed us that they nucleate in a direct contact with silicon. So there is no silicon nitride in between. And they nucleate as a pyramid, zinc blend pyramid at the beginning, and then from the side walls, these two arms appear and they are void. So because there is a different direct contact of this gallium nitride with silicon here, we have all phenomena, we have misfit dislocation, everything as expected is let's mismatch systems. Importantly, these wires are gallium polar. So point is that if we have these wires on silicon 111, they would be perpendicular to the surface. So we could not distinguish them from these regular ones growing on top of silicon nitride. Yeah, and then a piece of explanation how it works in our opinion. Imagine that we have some silicon oxide islands left on the surface. Then we expose the surface to nitrogen flux just to induce nitridation, and this islands acts as a mask. So this part is not nitridized. But actually, in the stem image, you see that this is the zinc blend island, the nuclei, first nuclei. Silicon nitride is here and here, while this part is not nitridized. Then you deliver gallium, and it's well known that gallium dissolves silicon oxide. So gallium collects here, dissolves silicon oxide, and remains as a droplet. And from this droplet, zinc blende gallium nitride grows, and then these two include nanowires. In that sense, what I'm saying is that residual oxide left on a silicon surface may lead to formation of gallium polar nanowires. We have checked this, the zinc blende inserts can be visible by X-ray diffraction, of course, not in a classical version, but using synchrotron in a special grazing incidence just to get insight into the surface only. And you see that if we use only HF, H, and single nitridation, so we suppose that these islands of oxide are still left and then grow on top of them, we have this cubic gallium reflections. But if the same substrate after HFF, nitridation, is cleaned with gallium and then nitridized again, these peaks disappear. So meaning that this residual oxide islands really cause a crystallization of this gallium polar nanowires. Okay, and a very nice message for us. If we use silicon, amorphous oxide on the top of silicon without any special preparation, we just get a perfect uniform polarity, nitrogen polarity. More than 400 nanowires were analyzed. All of them were perfectly nanopolar, nitrogen polar, so no mixed polarity at all. Okay, I think my time is over, so I will come to the short conclusion. I mean, aim of our work was to clarify how amorphous substrate, how the growth proceeds, self-induced growth on nanowires proceeds on a top of non-crystallized substrate. I mean, this is a little bit different from regular epitaxy, in which you have contact of two lattices and all this phenomena. So this is a little bit different thing. We have compared nucleation and growth mechanisms on two types of substrates, and conclusion is that mechanisms are pretty the same. Qualitatively, we have exactly the same growth mechanism on both substrates, meaning that probably we can expect that other substrates will show a similar behavior, and that this mechanism are actually typical to MBE growth method, plasma-assisted MBE growth method itself. However, quantitatively there are differences. Short incubation time on aluminum oxide and wider range of growth parameters to induce formation of nanowires. I try to explain this using experience studies, just to get information what centers might be responsible for this enhanced nucleation rate. Then we use this aluminum oxide buffers for SAG, and this was a good opportunity to show you importance of surface diffusion of gallium atoms, how strongly influence nucleation kinetics. And finally, last topic I discussed is a uniformity of polarity of nanowires grown on silicon. In particular, important message is that substrate must be perfectly uniform and clean. Otherwise, if you have islands of residual silicon oxide, you may expect mixed polarity in this case. So many thanks to all who contribute to this project. Marta Sobańska is our main grower, and actually she did majority of experimental work, I put it here. But we are also grateful to our collaborators from PDI, Vladimir and Dr. Sokolowski, who helped us a lot to understand phenomena and to describe them by the modeling procedures, and many other people. And of course, I appreciate financial support. And finally, I want to thank all of you for your kind attention. Thank you.
Thank you very much, Zbig, for the nice talk. My question is, can you actually observe coalescence of gallium nitride nanowires in your experiments?
Yeah. I
Yeah?
mean, I mean, I showed you that we see this in situ actually, because okay, I need to move a little bit. Okay, black curve here is a model which does not include coalescence at all. In real life, we observe this decrease of QMS signal, and this is due to the coalescence. I mean, we have explained that the point is that what happens during coalescence, okay, another way. You know that if you take a nanowire, gallium sits on a top face and close to the top surface, because diffusion length of gallium on a side wall is something like 40 nanometers, something like that. So all the rest dissolves. So nanowire is covered with gallium on a top surface and on a periphery, well, 40 nanometers long. Now, when you get into coalescence, what you actually do, you effectively reduce the surface available for gallium to sit. And this is what happened. Yeah, this is what you see here. This is how we explain this in this paper.
Yeah, it's perfectly clear. Thanks. Vladimir, yes, please.
First of all, thank you for your valuable talk. It's very interesting topic and quite broad review of all aspects. So my main question is about the nucleation on the amorphous surfaces. So what about the azimuthal orientation of the nanowires? I mean, in case of silicon nitride, they are all aligned azimuthally equally, so in the same direction. And what will happen in case of aluminum oxide? And there is the edge, I mean, the boundary between a random azimuthal orientation and epitaxial orientation.
Okay, you're asking about twist or tilt?
Twist.
Okay.
Tilt is clear. Tilt, there is many factors. Yeah. I see.
On aluminum oxide, twist is random, completely random. What we know from our previous work, this one, on silicon nitride, on nitridized silicon, that if we nitridate silicon at low temperatures, in this then on silicon, twist is also random. But if we expose the substrate to nitrogen plasma at high temperatures, then the twist is not longer random. I mean, there's epitaxial alignment, meaning that, okay, well, in terms of epitaxy, there must be then a kind of link between the wire and the substrate. So yeah.
Thank you. Thank you.
Frank?
Yeah, thank you, Zbig, for this very comprehensive talk. I have a small question about your XPS results, the nitridation of the amorphous aluminum. If I understood well, it seems to depend on the underlying substrate. Why is this?
Thank you, Frank, for this question. I expected it actually. Model is that incorporation of nitrogen to aluminum oxide depends on the concentration of oxygen vacancies. So in this case, I mean, in this case, you have plenty of oxygen vacancies available, while in this case, you have a supply of oxygen from sapphire. This is how we explain it.
All right, thank you.
And more precise model with creation of various phases is given right here in this paper. But this is a general answer.
Jean-Christophe, yes, please.
Yes, good morning. Thank you very much for this very interesting talk. And I have also a question on this aluminum oxynitride formation. So in your XPS study, so the sample was just exposed to nitrogen alone. Is that right?
Yeah, I mean, what we did, the sample was exposed inside MB chamber to nitrogen plasma for given time at temperatures which more or less corresponded to the incubation time or incubation conditions of nanowires.
Okay, so there was no gallium flux.
No gallium flux, yeah, in that sense, yeah. I mean, yeah.
No, but did you try an experiment where you keep the time shorter than the incubation time, and you expose to both nitrogen and gallium?
Yeah, okay, and I understand your point. Of course, this is important, but we haven't tried it. It would be really nice to do that, but then you need to go to high temperature just to keep incubation time long, yeah, and probably too low gallium flux. Okay, yeah, I mean, this would be interesting additional input. Yeah, I agree. Thank you.
Thank you very much. So I think I will address very similar question this afternoon. So that's why I was really interested by your talk.
Thank you. I'm looking forward to listen to it.
Any further questions? I don't see any further questions, so let's thank the speaker again, and let's thank all the speakers of the session, and we resume at 2 o'clock.
Thank you.
Moscow time. Yeah.